All right, welcome back. So we are going to look into chapter 17 today. So we have been talking about mechanical waves in the previous chapter, and most of the time we've been focusing on the waves in the either confined in the streams or within the air columns. Now, in this chapter, we'll shift our focus a little bit. We'll be focusing on the sound waves. Okay, so the physical phenomena of sound is defined to be a disturbance of matter that is transmitted from its source outward. Okay, so in this case, if you say you have a guitar string, you plug it, and then it will generate a sound wave. Okay, propagating outward in that sense. And when the sound wave hit our ear, then when we hear it, so the hearing process is the perception of the sound, okay? Just like the vision is the perception of visible light to our eyes, okay? So when this stream move to the left, it create compression to the left, okay? But then it leaves out the kind of diluted area on the right. So in this case, it propagates in this direction, okay? And then it also propagate in that direction as well. So what happens is it will go back and forth, back and forth. So if you look at one end of it, you'll see the sine wave being propagating outward. So the median as the carrier of the sound wave here, you will see, look at the air molecules, you'll see somewhere you'll have dense air molecules. On the other hand, you'll next to this, you'll probably find the loose kind of area of the air molecule. So the density varies as also as a function of time t, as well as the pressure, okay? Because pressure is directly proportional to the number of molecules in that sense, okay? All right, so then propagating back outward. So looking at a speak foam, which generate the sound wave. So that's the same high pressure compression rarefaction in that sense. Okay, for the low pressure area. Okay, and then the air molecules, you will see that as well. All right. So then you can describe the wave, sound wave, the similarly as we had earlier for the waves. So sine function, or if you like, you can do a cosine function. Okay, so doesn't really matter. And then when the wave hits our ears, it actually hit the eardrums inside the ear, and that create the force on it. So then the pressure um, oscillating of the information will be delivered or transmitted to the nerves that we can hear the sound. Okay, so because sound is a wave, so then you can expect to use those quantities that we describe wave. So wavelengths, t period of the wave, frequency, and the speed of the wave. Okay. So the speed of the sound in different materials actually varies. So it travels the farthest in solid metals and then decreases when you go to liquid or the least when you are in air. Okay, a particular number you'll be seeing or use often is the speed of sound in air at room temperature about 20 degrees. So that's about 340 meters per second. 343, which is about 770 miles per hour. Okay. The derivation of the sound of air, or the speed of air in sound, is detailed in the textbook. We can also quickly take a look here. So basically, because air is a fluid, so then if you have a column of air, you can expect the continuous of the flow applied there. So the amount of the fluid entering one portion of the pipe should be equal to the amount of the fluid exiting on the other side of the pipe. Okay, so then you also, if you do derivative of the mass, total mass over dt, that will also apply. So you come to the conclusion that rho, the density, times the air cross-sectional area times the speed should be equal to a constant because it's continuity of the flow. Okay, so in that sense, from this guy, you'll get one equation, so which I have it on my paper. I can show you guys. Maybe I should stop sharing so you can see this equation better. Okay, so continue the flow here. So rho AV at one portion of the pipe, okay? And assuming the area of the pipe is not changing, so at the other location of the pipe, then there's a change in the density. There's also a change in the speed, okay? So A and A will cancel out. So rho V will cancel out rho times V on the other side. And this rho dV and d rho V, okay, or V d rho, and then plus this times that. But because this is a small quantity, dV and d rho, right? So for the approximation, we'll actually ignore the higher order terms. So smaller terms times smaller terms, right? That's ignore that. So then this plus that will be equal to 0. So rho dV then equal to minus of V d rho, okay, in that sense, okay? So this is the result of continuity, and then we are going to use that result later. If you go back to your PowerPoint slide, look at the second figure on this page here. So if you have a sound wave that is propagating in air, take a look on say a cubic of the air here. So then in this case, rho TV, okay? So you should have the density of the air on one side and then density of air on the other side. There should be a change of it if you take a small portion of it, right? So plus dV or d rho. Temperature also would have a small change of dt, and the speed of the air will be having also the little bit difference deviation of dV, okay? So in a sense. So we can look at the force here, which is coming from the pressure difference, okay, of the air on one side and compared to the other side, okay. So force, net force, okay. Then go back to the my note here. So on one side you should have a pressure. On the other side you should have a difference in pressure, okay, deviation of pressure P plus dP. So dP could be positive, could be minus, okay. So it depends. So this is x, y, z, a small portion. So dx, dy, dz, small portion of the air molecule. So the net force on this portion of the air molecule should be equal to P times the area, dy, dz, minus the pressure on the other side times dy, dz, okay? And net force should be equal to mass times acceleration, okay? So in this case, because this guy, the net force is equal to, if you do this one minus that, right? So P dy dz cancels. So then the result will be minus dP dy dz, dP dy dz here. Okay, so force equal to that. Now divide both sides by mass. So then you get acceleration equal to dP dy dz over m. Okay, the mass here should be the mass of this whole thing. So rho dx dy dz. Okay, dy dz, dy dz will cancel. So then this will become minus dP over rho dx, okay? So A, acceleration being dV over dt. So then dV over dt equal to minus dP over rho dx, okay? So if you move dt to the other side, so then dV equal to dP over rho dt over dx. Now dx over dt is v, right? So dt over dx then is 1 over v, okay? So now you can see you have dV equal to minus dP over rho times 1 over V. So you can do rho to the other side. So rho dV equal to minus dP over V. Okay. And here, so rho times dV, if we go back to the top of the page here, rho times dV is minus V d rho. Okay. So then rho dV minus V d rho, okay, equals to minus dP over d rho. So V squared then, so minus minus cancel. So then V squared equal to dP over d rho, okay? So that tells you V is equal to square root of dP over d rho, all right? Now, for the, if we take this small portion of the gas. Okay, so then everything, because this is a small portion, so then everything will happen just quickly. Okay, so dt will be small time, right? And then so from one side to the other side, right? The air molecule goes there, happens quickly. So then you can think this as a adiabatic process because there will be no time for the any heat to escape. Okay, so then if this is a adiabatic process, then PV gamma equal to constant, where gamma is equal to Cp over Cv, which is 7/5, because air is being mostly diatomic gases, is made of 20%, about 20% of oxygen, and then about 79% of nitrogen, etc. Okay, so then this guy is equal to 1.4 for air. The mass is equal to number of moles times molar mass. V will be mass over rho. So M times capital N times M, capital M over rho, okay, to be the V. So if you take V as that guy, okay, so then P times NM over rho to the gamma will be equal to constant, because this is constant, right? And then for the fixed amount of that guy, that's also constant. Okay, so for a small portion of that, so that's also constant. So you should get P times 1 over rho to the gamma equal to constant. And if you take natural logarithm of this equation, so you get natural logarithm of P minus gamma, natural logarithm of rho equal to constant. Okay, and then if you take derivative of both sides with respect to rho, on this side it's got constant, so it can become 0. Derivative of this over rho will become 1 over P dP over rho. Okay, and then on this one will be gamma over rho, d rho over d rho. Okay, so this will become 1 in a sense, doing the derivative according to chain rules. So dP, so then you get basically this is what you get. This is 1. So then this equal to that. Okay, so basically this part equal to that. So equal. Okay, so then rearrange the terms. dP over d rho will be equal to gamma P over rho. Okay, now dP over d rho is what we need for speed. So then speed equal to square root of this thing. Okay, so the speed equal to gamma P over rho. According to ideal gas law, PV equal to nRT. Okay, M is the mass divided by M. Okay, RT. P then equal to M over V, RT over M, over capital M. Okay, so this over there is rho, RTM. Okay, so because of dP over d rho is equal to gamma times P over rho, which we got on the previous page at the end there. Okay, so V equal to square root of that, or this here. dP over d rho is equal to this guy. Okay, so then this is gamma, P being that guy. Okay, rho and rho cancel, so then equal to gamma RT over M. So V then equal to square root of gamma RT over M. Now for air, again, gamma is 1.4, M is 28.97 grams per mole, so 0.02897 kilogram per mole. R is 8.31, and if you take T as 20 degrees Celsius, which is 293 Kelvin, taking that into here, it turns out the speed of the sound in air will be 343 meters per second at 20 degrees, okay? And so if we are talking about in general relationship to time t, right? So in this case, so we can use 20 degree as a reference, okay? So 20 degree as a reference, you kind of manipulate this guy, right? So then square root of T over the 20. And that should be the 20 degrees in Kelvin. It'll be 270 degree Kelvin there. Plug in those constant numbers there, and then T over 273K. Okay, so it turns out to be 331 meters per second over square root of T over 273K. Okay, so this is acting as a reference. Okay, so you get then speed equal to that guy. All right. So a little bit deviation there. Let's go back to the PowerPoint slide. So the result then is the speed of the sound in air. Okay, it's this guy, as we saw in the derivation. All right. So if we use root mean square velocity of the speed, which is this guy. Okay. So or if we look at that, so this is what we learned in the ideal gas law, the theory of ideal gas law, the kinetic theory of ideal gas law, which we found that so these two kind of in agreement with each other because you have T, okay? You also have T there, okay? Where in this case, K is 1.38 times 10 to the minus 23, okay? And then if you plug in the mass as the mass for a single air molecule, or shouldn't say that, but on average, for the average, I should say the average of the air molecule, okay? Because it consists of oxygen and nitrogen in that sense. The average mass for one equivalent air molecule. Let's put it in that way. All right. Okay. So now, because sound is a wave, so then when we talk about wave, we know there's if there's a wave, there's energy in the wave, right? So here is the same thing. So there will be energy in the wave if the wave hits an area of A in the time of t, then the intensity the area receive will be the energy of the wave divided by the area divided by time t. Okay. And if you have a sound given out by a point source, remember that power equal to energy divided by T, so then intensity should be equal to power divided by area, okay? So area, if it's sound is emitted by a point source, then the area is the spherical area, which is 4 pi r squared. So I then equal to P over 4 pi r squared, okay? The intensity has the SI unit of watts per meter square. Okay, so that's what we learned earlier in the previous chapter as well. So once you get the intensity of the sound, then as we hear that sound, so our ear actually hear sounds a little different. Instead of its increment in the intensity itself, it actually hears, we can actually discern the sound's intensity by the intensity level, which you call beta. And that's in the unit of decibel. It's equal to 10 decibel times log of the intensity, actual intensity, divided by a constant intensity, which is the faintest sound that we can hear. That intensity is 10 to the minus 12 watts per meter square. Okay. So in that case, if you have the intensity, you can calculate the decibels, okay, or the intensity level of the sound. So here is the intensity levels, a figure of it. So the threshold is 0 decibel, okay. Now, if you are out in the nature, so rustling a leaves is about 10 decibel, and then if you whisper into someone, it's about 20. A normal classroom is about 50, okay? A normal conversation is about 60, heavy traffic is 70, subway will be 100, and as it gets louder and louder, you'll feel that differently, okay? So from 10 to 20, let's take that as an example. So the intensity actually level is only twice, but it's actually 10 times louder. Okay, in that sense, because you are doing logarithm of it, the intensity over I naught, okay? So in that sense, I have a video link here for you guys to see gives you real life examples, the loudness of sounds in history and then in terms of decibel as well. Okay, so when the sound is in having large intensity or intensity level is too high, you actually start to feel the pain in your ear, and then if you stay to listen to louder sound, it eventually will rupture your eardrum, then you cannot hear anymore. After that, you become permanently deaf. Okay, but check on the radio. It's very interesting. Okay, I highly encourage you guys to do that. But let's take a look at the example here. So it says a crying child emits a sound with an intensity of 8.0 times 10 to the minus 6 watts per meter square. It says find the intensity level in decibels for the child's sound. B, if this child has a twin and both of them crying at the same time, what will be then the intensity level? Okay, so let's take a look. So we are looking for intensity level, beta. So the formula to use is beta equal to 10 decibel log of I divided by I naught, where I naught is 10 to the minus 12 watts per meter square. Okay, so it should be straightforward. You just plug in the intensity here to calculate it. Okay, so this will be 10 dB log of 8.0 times 10 to the minus 6 watts per meter square over 10 to the minus 12 watts over meter square. Okay, plug in those numbers into your calculator, you should find this as 69 hertz dB decibel. Okay. Now, second part, if both of them climb, then intensity doubles, right? So beta now equals to 10 dB log of 2 times 8.0 times 10 to the minus 6 over 10 to the minus 12. Okay, and it turns out to be, so it doesn't double that, but it turns out to be 72 decibel. Okay, so as it doubles, it increases about 3 decibels for the intensity level. All right. And let's go back to the slide and take a look on a second example for today. So this one says residents of Hawaii are warned of approach of a tsunami by sirens mounted on the tops of towers. Suppose a siren produces a sound that has an intensity level 120 decibel at a distance of 2.0 meters, treating the siren as a point source of sound and ignoring reflections and absorptions. Find the intensity level by the observer at distance of 12, 21 meters from siren, and then see how far can the siren be heard. Okay. So it says when you are at 2 meters away, the intensity level, so beta, let's call beta at 2.0 meters like that, beta sub 2.0 meter is 120 decibel. Okay. You are looking for beta at 12 meters and then beta at 21 meters. So we know beta equals to 10 decibel, right? Times log of intensity divided by the constant number, 10 to the minus 12. So that means if we can find intensity at 12, right? Then we can calculate that beta. And then if we can find intensity I at 21 meters, we can also calculate this beta at 21 meters. Okay, so the key is to find intensity. Now intensity, because this siren is mounted on the top of tower, so you can treat as a point source. So P over 4 pi square. Okay, so if you can find P at the source, then you can calculate I at different locations, right? Now it tells you this guy, so you can actually calculate I at 2, right? By plugging this is a 2, and then use this one back to calculate what will be I at 2, right? Because beta at 2 meters is equal to 10 decibel log of I at 2. Let me just say I sub 2, right? Over I naught, which is that number. And that's equal to 120. So you can calculate I2, right? So once you have I2, plug it in here, and then this is 2, so you can calculate the power at the source. Once you have power, you can calculate, right? So I think that's one way of doing it, okay? So you guys can do that, no problem. But I'm going to do this a little bit differently, okay? So then I will not need to calculate P actually. So I will just look at the I equal to 2, so I equal to 2, I at I equal to 2, that is actually equal to P divided by 4 pi times 2 square, okay? Now I at 12 is equal to P then divided by 4 pi 12 square, right? So then I2 and I12 actually have just a relationship, right? So you can do the ratios, you can figure out the relationship. So this one is smaller than that guy. So for my beta at 12, let me just say sub 12, okay? That should be equal to 10 dB log of I12 over I naught. So looking at these two, I2 over I12, it will turn out to be, so this over there. So it turns out to be, so cancel, right? P cancel P, 4 pi cancel 4 pi. So then it will be 12 to the square over 4. So 12 square over 2 square. So this is like 6 square, right? So 36. So I12 is equal to 1 over 36 of I2. Okay, so that's basically what it is. So then this becomes 10 dB log of 1 over 36 of I2 over I0, right? So it's that times that guy. Okay, so now it becomes 10 dB logarithm of 1 over 36, okay, and plus log of I2 over I0, right? So you can calculate this times 10 and this times 10, but this times 10, right, is the 120, okay? So it's basically this first plus 120. So this gives you minus 15.6 dB plus 120 dB on the second. So it gives you then 104 dB, okay, at 12 meters away. Similarly, you can do to the I21. So I21 is equal to P over 4 pi 21 square. Okay, so you can do the ratio. It turns out to be, so I pop B, beta 21 is equal to 10 dB log of then I21 over I naught, which I21 over I2 is, so if you do I21 over I2, okay, so then this over that P 4 pi cancels, so then it'll be 4 or 2 square over 21, so it's 2 over 21 squared, okay, so this is then 10 dB log of, basically this is in the place of 1 over 36, so 2 over 21 squared plus 10 dB log of I2 over I naught, which is 120, okay, so that's 120. So then this would be minus 20.4 dB plus 120 dB, which gives you 99.6 dB. Okay. All right. Now Parsi is asking how far can the siren be heard? Okay. So it's not talking about the threshold of I naught, right? So it's basically asking you when your I is equal to the I naught, what will be the R? Okay. So in this case, so then excuse me. So I will be equal to 4, sorry, P over 4 pi. Now in this case, R square, okay? And I add 2 again will be P over 4 pi, but 2 square. So we can still do I over I2, which will be giving you, again, cancellation. So it will be 2 over R squared, okay? So what happens here is now for the intensity level, beta at R is 10 dB log of IR over I2, okay? That is 10 dB log of now just 2 over R squared plus 10 dB of log of I2 over I naught, okay? So, and this should equal to 0 because that's the threshold. If you go 2 slides above, okay, that's intensity level can be heard as 0. So that means this is 120, right? So that means this is minus 120, okay? So then you can solve for this. So this thing is minus 120, so that means log of 2 over R to the square is minus 12, okay? So it becomes, so 2 on here, it becomes 2 in front, okay? So 2 times log of 2 over R equals to minus 12. So then log of 2 over R is minus 6. So 2 over R then equal to 10 to the minus 6, okay? So then R equals to 2 times 10 to the 6 meters. Okay, so that's how far you can hear the sirens. Of course, this is assuming no reflections, no absorption. Okay, so in reality, the air will absorb a lot of energy, and then when the siren hits somewhere, it will be reflected. Okay, so further decrease in the intensity. All right, so we'll stop here for today, and then we'll come back another time. Okay, so um, I'll see you guys. Bye.